Nicholas Krubble, and we're going to talk about land subsidence for groundwater hydrology 566. Be talking today about what is land subsidence, how it relates to groundwater, what real-world data looks like, and sort of the mathematical framework and sort of how we model it. I have some animations in here. Those are all based on the mathematical framework, all presented at the end. And the real-world data is going to be from the Central Valley. Subsidence or land subsidence is the sinking of land. It's fairly simple concept. It's the dropping of an area of land. It's most often caused by the removal of water, or oil, natural gas, mineral resources. Those being taken out of the ground destabilizes it and can cause compaction. There's also some causes from tectonic plates, but those are much, much smaller. So from groundwater pumping, you can almost drop a meter a year in really seriously affected areas. As you can see on the right-hand side, that's just showing from 1925 to 1977. That's all caused by groundwater pumping. Tectonic plates movement and their land subsidence maybe causes a millimeter every 100 years or so. It's very slow. But groundwater pumping and fracking and oil drilling all cause subsidence at much, much faster rates. It damages buildings and infrastructure and increases the risk of flooding, collapses aquifers, meaning they can't be refilled, and can hurt aquatic ecosystems. Thinking about the effects on groundwater flow, it's important to understand that subsidence occurs mostly from pumping water out of the ground, and that's where we care about it. But it has a meaning. The groundwater cycle has a meaningful impact on subsidence itself, and you can actually sort of abstract some information about how groundwater flows in the area by looking at their subsidence data, because even places that are not sinking will move a bit, and that can tell you some interesting things. And we'll see that when I show real-world data, what it actually looks like on the ground. The compaction itself also affects the flow. So when aquifers collapse, it can dramatically impact how groundwater flows, the base flow outputs. All of these can be disrupted. It can increase it in other areas. And so it's an important factor to understand how it functions and sort of how it works. So I made some animations to sort of demonstrate what subsidence looks like in the real world. This is a fairly simple one. The material is homogeneous, and the compaction rate is fairly quick. It's about 1 meter per decade, which is not unheard of. In fact, it can be much faster than that. But here in a completely homogeneous material, you see a very strong deformation around this area. It's also the surrounding areas measured in kilometers. And I'll show a much more complex version of this, but I just wanted to show what it might look like from a side view. So I wanted to show some real-world subsidence data. What does it look like out in the wild? And so here, this is a location in the Central Valley. This is a single location over 20 years. You can see the linear trend means that it sinks about 3 meters per the 20 years that I'm looking at here. But you'll note that the subsidence rate is not consistent across it. And you can actually tell droughts here. So in 2015, there was a major drought in this area. And in 2022, there was also another drought. And so you can see that although there's some constant pumping that is occurring and dropping at a much slower rate, during these drought times, you see this dramatic drop. So these are places where subsidence almost, like 60 millimeters that year. It's a pretty high rate. And it reflects that change in groundwater. It's an interesting thing to look at. So this is another example of real-world data that is also affected by subsidence. This is another location in the Central Valley. So we're looking at the same 2 droughts periods, 2015 and 2022. But in this case, you can see the difference not only in this upward graph, but I'm also showing the distribution because you can tell when these drops occur. I know the subsidence data is normally distributed. I'll show a better example of that later. But here we have a slight drop here, 2015, and you can see that reflected as it shifts over the curve, and it's relatively stable. It's still moving downward, and there's likely some secondary compaction over the years and continued groundwater pumping. But you can see a significant change as we get into the 2022 drought. And so there's been a huge increase in pumping, and there might even be secondary compaction factors here, failures of aquifers. It's pretty significant, but you can also see it in the distribution as it shifted over quite a bit. So I thought it was interesting to show an example without subsidence. Is outside the Central Valley, and it's still this daily measurements. You can see that this data is normally distributed. And just a note, so the 0 is picked from when the station is started. So the way these measurement tools are, they zero them out when they start these measurements. And so based on the place and the year it started is why it looks like it's shifted off the 0 line. But there's still, you can see from the linear trend, there's no change over the years. But it also shows sort of how groundwater flow might affect it throughout the year. Obviously it's not consistent. The mathematical framework I'm using to model subsidence that is put into the animations that I have is Tezagi's 1D consolidation. Hydrologists often modify this to only use this compressibility index based on a hydraulic head change. This is because in order to calculate the compressibility and variability due to head change, you have to know a bunch of factors about soil compressibility that you don't necessarily always know, so it might be better just to estimate a single thing than to pretend as though you know a bunch of things you don't. This is a 1D consolidation, but you can spread it out such that it's 2D over an area, but you get no lateral movement from this equation, which is somewhat problematic. I'm going to show over more in depth of how you walk through this. Okay, so in order to put Tezagi's all together, you need the flow in the material, you need the hydraulic gradient or the change as this flow occurs, and from that, you're able to calculate the volume change due to the flow. And then once you have that volume change, you're then able to calculate the volume change from the phase relation. And so this is the volume change in the soil, essentially. And then you get this coefficient of consolidation from the soil properties and what you've seen in the phase relation. And then you combine that in the final Tezagi's equation, in this differential equation, to get the final compressibility change. This can be positive or negative, depending on whether water is flowing in or out of material. This is very simplified. It's a 1D, no lateral movement. But in terms of the actual compaction calculation, it's fairly good as long as your material is homogeneous. And we've actually done work, putting layers so that you're only in a small section of the material are you assuming that it's homogeneous. But this is actually not what's most commonly used. There's often a more simplified version of this that hydrologists in particular like to use because the geology of a material is very hard to tell. And so it's much easier when you're simulating this to just assume a coefficient of consolidation or to data mine for that coefficient and not actually worry about the underlying soil mechanisms that much. Okay, to wrap up this presentation, I wanted to show a much more complicated version of subsidence. We talked about what is subsidence, how groundwater flow is affected by it, what real world data looks like. But I think the most interesting part of this, especially from a researcher perspective, is how do you model it? How do you think about it in the real world? And how do we anticipate it? And so this is using Tezagi's to its fullest potential, where I'm differentiating on little grid cells. And so I'm able to put in sort of this heterogeneous geological formations. Although I will say this is a single well example. And so here you can sort of see the effect of differing geologic formations affecting it differently. There's still no lateral movement, but it's a much better representation of how groundwater actually moves, and hopefully it inspires you to model it even better.